Hello and welcome to lecture 24, NPTEL online certification course on aero engine gas turbine cycles. In last lecture, we were discussing about the limitations of turbojet engine. We were discussing about the expectations from the new engine configurations, basic types of turbofan engine. We were discussing about advantages of turbofan engine. We also were discussing about the selection criteria for the bypass ratio and fan pressure ratio. So, here in this case, as we look at carefully, say we have configuration where it shows we have 2 spool turbojet engine, we have 2 spool high bypass ratio turbofan engine, where we were discussing about the difference in terms of construction. So, just look at here, what we were discussing is in terms of having say larger diameter fan which is been placed in the front of the core engine or say turbojet engine, that we have defined as a high bypass ratio engine, where we were having primary stream and secondary streams. What all are the benefits that we have discussed? We have realized this kind of configuration that will permit us to use or to go for higher turbine entry temperature. This permit us to reduce the noise. It is also helpful for reducing the IR signature, both for say high bypass ratio engine as well as for the low bypass ratio engine. Now, let us move ahead what all we see in terms of say bypass ratio engine. So, here if we look at this is representing Su-30, where we have used say Saturn engine, it is low bypass ratio engine. Say if we look at for this fighter, we are having 2 engines which are being placed inside this. If we look at this is representing Trent 970, which is fitted with say jumbo jet A380. We have 4 such engines which are being placed. These engines are high bypass ratio engines. We also have low bypass ratio engine which are being used for say military purpose. This is for Nirbhay missile. We have used here the Manik engine, it is called STFE, small turbofan engine. So, we can say this turbofan engines, they are having wide range of applications. Now, let us look at the low bypass ratio turbofan engine first. What it says, this low bypass ratio engines, they are having higher fuel efficiency, and this higher fuel efficiency is because of incorporation of bypass duct and more efficient combustion, because of which we are having lower fuel consumption, and that is what will be lead to improve the fuel efficiency. We also have the reduction in noise compared to turbojet engine because of mixing and slowdown of exhaust gas. That is what is been covered by say cold air coming out from our secondary duct. Similarly, we are having enhancement in terms of low speed operation, because we have bypass fan which will be generating the additional thrust, which will lead to give us low speed operation, suppose say takeoff and landing. It also improves the acceleration and short takeoff distance. That is the reason why this permit us for the aircraft engine to operate at shorter runways. The low bypass ratio engine, that has enhanced the power as well as thrust, because we are having the additional bypass fan and efficient combustion process. That is what will lead to increase the application of such engines for the military purpose, where we are looking for high performance capabilities. At the same time, because of bypass fan and improved combustion efficiency with say lower operating temperatures, that is what will lead to reduce the stress, wear and tear of the engine, and that has improved the reliability of the engine, and that is what has given more permeability to use such kind of engines for aero applications, and they are more versatile both in terms of subsonic operation as well as supersonic operation, and that is the reason why such engines have application for fighters, business jets and smaller commercial aircraft. So, in overall, if you will try to look at, it says we are modestly increasing the diameter compared to turbojet engine in order to accommodate our bypass fan. This is having capability to fly at supersonic speed with minimum thrust drop at high speed and altitude. They are more efficient compared to turbojet engine when they are operating at the subsonic condition, and that is what has led to give the attraction towards say low bypass ratio turbofan engine in compared to turbojet engine. But still here in this case, since my exhaust velocity coming from the core engine is at high magnitude, that is what has led to increase the noise. It is little complex to accommodate the dual shaft configuration. If we look at carefully, rather I say single fan, it may be possible that low bypass ratio turbofan engines have say more than one fan, maybe one fan, three fan kind of configuration, and that is what will be lead to increase the complexity in terms of construction. So, here in this case it is little inefficient compared to turbojet because of higher cross sectional area, and at the same time supersonic speed capability is poor compared to this turbojet engine. And the question always will come like what next, what will be the solution for that. Let me tell you here, when we are talking about the special application, some of the cases, some of the points we need to compromise, and this compromise mainly we are doing in terms of military applications, where our requirements are of special kind, where we cannot compromise something in order to gain something. Okay. So, under that configuration always turbojet and turbofan engine with low bypass ratio have major attraction. Now, let us move towards say the types of turbofan engine. So, we have seen the classification of the engine in last lecture. Now, let us put this classification in other way. It says we can put the types of turbofan engines as forward fan unmixed single spool configuration, forward fan unmixed two spool configuration, where fan and low pressure compressor they are on one shaft, high pressure compressor and high pressure turbine they are on one shaft. Fan will be driven by LP turbine and compressor will be driven by HP turbine. Geared fan will be driven by LP turbine and compressor will be driven by HP turbine. Next, what we have is forward fan unmixed 3-spool configuration. We have forward fan mixed flow configuration, where we have without afterburner operation and with afterburner operation. We have one more classification in terms of aft fan. We have turbofan engine with intercooling and regeneration, vertical takeoff and landing kind of configuration, where we will be having swelling nozzles and switch-in deflector system. So, these all are the types of turbofan engines which are existing at this moment. And for this course, we will be focusing more on this 7 classification. So, you can say this all are the possibilities with our turbofan engines. So, we will look at what all are the benefits of individual configuration. When we say fan and LP compressor on one shaft, fan is driven by LP turbine, geared fan will be driven by LP turbine, we have 3-spool configuration. So, you can understand as per the requirement, the people they have developed these engines, and over the year we are having lot of development, that is what is existing, and lot of development, that is what is going on. Okay. So, for today's lecture, let us target very first engine. It says forward fan unmixed single spool configuration. So, now let us try to understand what we mean by forward fan and unmixed configuration. So, here if you look at this is representing say fan, it is placed in forward direction, that is why it is a forward fan configuration. And we have two nozzles, one we say is a core nozzle or hot nozzle, second that is what is my fan nozzle. These two nozzles they are not mixing, that is the reason why it is called unmixed configuration. We will see when I will be discussing about the mixed configuration, it has its own value, it has its own meaning. So, there are engines in which we will be having hot gas as well as this cold air, they will be mixing together and that will be coming out as exhaust using single nozzle. So, that is what is called mixed kind of configuration. Let us not discuss at this moment, let us put it as say confidential part and let us start discussing about the working of this engine. So, here in this case we have our initial component, that is inlet duct or say inlet diffuser. So, on our diagram let us put this case. Now, you are expert enough in order to understand ideal cycle and actual cycle. So, let us discuss about the ideal configuration. So, we can say my air, that is what will be entering from the intake and that will gain some pressure in my intake, we can say where there is a deceleration of flow which is happening. So, remember one thing, as we have discussed earlier in turbojet engine also, at the entry of my engine, let it be fan or let it be compressor, my flow need to be subsonic. Okay. Let your aircraft will be flying at supersonic speed, but at the entry my flow need to be subsonic condition, means I need to decelerate my flow from supersonic flow to subsonic flow. Okay, and that is what we say as a diffusion process. Diffusion is nothing but it is increase of the pressure. So, that is what we are doing here from infinity to P02. This is representing the actual process. Now, very first it will be passing through the fan. This fan we can see it is comprising of rotor and this is stator. Okay. Many times people they used to say vanes also, but you can say it is comprising of rotor and stator configuration, where I will be having the rise of pressure from 2 to 8 or P02 to P08. Now, look at carefully here, what compression which is happening inside my fan, this compressed air will be passing through this bypass duct, same compressed air with some quantity it will be entering inside this core engine. Okay. So, at the entry of my compressor my pressure will be P08, do not forget that part. Okay. So, now I will be talking about my actual process from 2 to 8. My next component here it is compressor, and this compression process we are representing in terms of 8 to 3. Just look at carefully, do not get confused here. Say from where the air is entering or what is the entry pressure to this compressor. This entry pressure is nothing but the exit pressure coming out from the fan. Okay. Now, next component what we have is our combustion chamber. We know that combustion is taking place at the constant pressure, but in actual case we will be having some drop of pressure. So, actual process is represented as process 3 to 4. The component what we have 4 to 5, it is our turbine, and this turbine for this case also it is mainly been used to rotate the compressor as well as fan, since we are having only one spool. Okay. So, here this fan, compressor and turbine they are on single spool. Okay. So, this turbine will be generating sufficient amount of power in order to rotate fan as well as compressor. So, this is representing my expansion process which is happening in our turbine. It says 4 to 5. We have our say connecting duct, or we can say tailpipe, and 6 to 9 which is representing my nozzle. That nozzle is hot nozzle or core engine nozzle. So, this is representing expansion which is happening inside the nozzle. Now, let me ask you a question here. We have one nozzle, that is what is with the core engine. We have second nozzle, that is what is with my fan. So, here if you look at my fan, that will be having exit pressure as 0.8, and the exit condition from our nozzle, that is nothing but this 10. Okay. So, how do we represent this expansion which is happening inside the nozzle? Any guess? Can you represent process 8 to 10? Okay. Let us see. Here this is represented from 8 to 10. So, be careful, this is representing my fan nozzle expansion process. Okay. So, this is what is a change compared to your turbojet engine. So, do not get confused, just number these stages such that you will not get confused in terms of putting the stations on TS diagram. Okay. I am sure you got the idea about this process now. So, let us try to realize the actual cycle. So, very first process what we say is intake or the inlet. We say that as a infinity to 2 process. Here in this case we can say we have our diffuser. For diffuser, the component efficiency we say as a diffuser efficiency. This diffuser efficiency we can correlate in terms of pressure ratio. So, this P02 is representing the exit pressure from the diffuser. Similarly, we have discussed this many times in terms of say my process. This process is adiabatic process, and that is the reason why my H02 and H01 they will be same. So, based on this we are able to calculate our exit pressure and exit temperature from the inlet. Now, let us move towards the next component. What next component we have is our fan. So, fan, as we have discussed, it is same defined as our compressor component, but here in this case my diameter will be larger. So, for the fan also we can write down the efficiency, since it is a compression process. So, we can correlate that in terms of say polytropic efficiency and my fan pressure ratio. Here there is a purposefully we have kept the polytropic efficiency. Suppose if I consider this engine is a low bypass ratio engine, where I may have 1 or 2 fan or maybe 3 fan, depends on our requirement. There we will be having individual efficiency. That is the reason why we have kept this as a polytropic efficiency, else this can be defined as our adiabatic efficiency of the fan. Now, that is the case, we can represent our fan pressure ratio or compression ratio as P08 by P02. Now, we know we can write down this in terms of temperature ratio also. So, this temperature ratio we are defining in terms of efficiency as well as pressure ratio. By doing so, we are able to calculate what will be the pressure and temperature at the exit of the fan. Okay. So, be careful in terms of putting this equation. Now, let us move towards the next process. This process we are writing as process 8 to 3. So, be careful, as I have discussed earlier, my entry pressure and entry temperature of the air to my core engine is station 8, and exit of compressor it is station 3. So, we can write down our compressor efficiency by this equation, where individual stage may be having say individual polytropic efficiency. So, by that mean we can calculate our compressor efficiency. Now, for this case, as we have discussed, these efficiencies of the component we are assuming, and what numbers need to be assumed, that also we have discussed in first week. So, you are clear with all this idea now. We can say this is representing our compressor pressure ratio, temperature ratio, and based on that we can calculate what will be our exit pressure, what will be our exit temperature from the compressor. Okay. Now, next component what we have is our combustion chamber. This combustion chamber with the control volume, we can say my energy which is entering inside is m dot core H03. Be careful, the mass flow rate which is entering inside my core engine is m dot core. It is not m infinity. Here this is representing our burner efficiency and the amount of fuel what we are burning and fuel mass flow rate, and at the exit it will be coming out with m dot core plus mf H04. So, for the combustion chamber we know there will be drop of pressure, and that drop of pressure will give us what will be the exit pressure from the combustion chamber. Now, let us put the equation in terms of energy balance. So, we can say we are putting energy in, that is m dot core H03 plus m dot burner efficiency into calorific value, and this is representing my exit condition. If we will simplify this equation, it says my fuel air ratio, it is given by H04 minus H03 divided by efficiency into calorific value minus H04. Be careful, here also my fuel air ratio is m dot f divided by m dot core, it is not m dot infinity. This m dot infinity is a total air, that is what is entering inside the engine. Our interest here is mainly say the combustion we are doing with this m dot core. So, that is the reason my fuel air ratio equation will be different. So, based on that we can calculate what will be my fuel air ratio, we can calculate what will be our exit pressure, turbine entry temperature may be known to us. There are different configurations of the engine. People they are targeting with say specific fuel consumption to be certain number, and for that specific fuel consumption they will be giving us the value of fuel air ratio, and under that condition maybe we need to target the turbine entry temperature. So, be careful, do not go blindly by this formulation only. It may be possible rather giving turbine entry temperature, the fuel air ratio is given to you. Okay. Now, let us move with the next component, that is our turbine. This turbine expansion process we are representing as process 4 to 5. Now, as we have discussed, my turbine work, that is what is used to rotate both compressor as well as fan. So, I say Wt, that is equal to Wc plus Wf. My Wt we are writing as say m dot core into 1 plus f Cp T04 minus T05, that is equal to, for this compressor we need to be careful, it is m dot core Cp T03 minus T08, be careful, and for fan this is m dot core into 1 plus beta Cp T08 minus T02. See here this mass flow rate which is entering inside the fan, it is given by m dot core into 1 plus beta. Do not commit mistake here. Okay. If this is the case, we know what is our beta, we can calculate what will be my temperature ratio or what will be my exit temperature from the turbine. We have definition of our turbine, that is what will be giving us the idea to calculate say what will be our pressure ratio. So, this pressure ratio that will give us the idea for the calculation of our exit pressure from the turbine. Okay. So, be careful in terms of calculating say turbine exit temperature and turbine exit pressure. Now, what we have next is say tailpipe, that is what is say entry of the nozzle. If we consider, since it is a say duct where we will be having drop of pressure which is happening, this drop of pressure we can say as say delta P. Okay. The next component what we have is our nozzle. This nozzle I say here for turbofan engine we have two nozzles. First it is say my turbine nozzle, that is what I say 6 to 9 or core nozzle, and second that is what is my fan nozzle, it is represented as say from 8 to 10. So, we have done the calculation earlier also for the turbojet engine. So, let us try to understand what need to be done for this nozzle calculation. So, what we know for nozzle we need to do the calculation for the critical pressure, and then we need to compare that with the atmospheric pressure, and we need to check whether our nozzle is choked or unchoked, and based on that we need to select the exit pressure. Now, based on that exit pressure we will be calculating our exit temperature, and from that exit temperature we are calculating what will be our exit velocity. So, let us look at, suppose if I consider we have our turbine nozzle. For this turbine nozzle we can say critical pressure ratio, it is a function of the turbine say nozzle efficiency. So, this nozzle efficiency, as we have done the calculation for the critical pressure, if I say my critical pressure is lower than the atmospheric pressure, we know we can say our nozzle as unchoked nozzle, and for that my exit pressure will be atmospheric pressure. And if this is the case, we can calculate our exit temperature based on the temperature ratio, and we can calculate what will be the exit velocity using this formula. Okay. This is what is similar to what all we have done for the turbojet engine. Suppose if I consider we have our configuration where the critical pressure is greater than that of our say atmospheric pressure, we say that as a nozzle under the choke condition, we can say exit pressure equal to critical pressure. We can calculate what will be the temperature ratio, and from that temperature ratio we can calculate what will be our exhaust velocity. If you have any doubt how these equations are coming, I suggest you to repeat your week 2 again in order to understand these formulations. Okay. Now, let us go with the next configuration, it is with my say fan nozzle. For this fan nozzle, the process we are representing as say 8 to 10. We will be calculating our critical pressure ratio. Again we will be checking whether critical pressure is say greater or less than that of the atmospheric pressure. If we say my critical pressure is lower, we can say nozzle as unchoked nozzle, and our exit pressure will be atmospheric pressure. Based on that we will be calculating our temperature ratio, and we will calculate the exit temperature, and from that exit temperature we can calculate what will be our exhaust velocity. Now, look at here, suppose if I consider critical pressure is greater than that of the atmospheric pressure, under that configuration we know our exit pressure we will take as a critical pressure, and we can calculate our temperature ratio. Same way, by using this equation we can calculate what will be our exit velocity. Okay. Now, we know this all cycle parameters in terms of pressure, temperature, velocity, we are doing calculation in order to calculate our performance parameter. That is what is our main target. Okay. So, let us look at how do we use this data. Now, here in this case for turbofan engine, my net thrust, that is what we are writing as a cold thrust plus hot thrust. So, what we mean by cold thrust? This cold thrust is because of this cold air coming out from this bypass duct and with nozzle, and hot means that is what is coming out from our core engine. So, if I say cold, that means it is given by m dot f V10 minus V infinity plus A10 P10 minus P infinity. So, here this is representing my cold thrust. Same way for the hot thrust, it is given by m dot core into 1 plus f V9 minus V infinity plus this will be my say pressure thrust for the core engine or hot thrust. Okay. So, be careful in terms of the calculation for turbofan engine. Similarly, we have our terminology called thrust specific fuel consumption. So, that is given by m dot f divided by thrust. This m dot f, it is nothing but f into m core. Be careful, this is not our free stream air or air mass flow rate which is entering inside the engine. This is basically which is passing through our core engine. In terms of terminology for the propulsive efficiency, we are writing here as V infinity into thrust, but the thrust we are writing as total thrust. It is hot thrust plus cold thrust. Okay. Similarly, in the denominator we will be having hot thrust plus cold thrust. Now, exit kinetic energy for this configuration is given by m dot core 1 plus f V9 minus V infinity square. So, we can say this is what is from our core engine, and this m dot f fan into bracket V10 minus V infinity square, this is what is for our fan nozzle. So, this we need to be very careful about. Okay. This can be represented in terms of bypass ratio also. So, whatever is suiting, whatever is preferred to you, you can remember this equation. So, these equations need to be remembered by us. Okay. There is no other alternative. Okay. Next, that is what is our thermal efficiency. In line to what we have taken the denominator for propulsive efficiency, we know that will be the numerator for the thermal efficiency divided by m dot into QR. It is nothing but the amount of heat input. Okay. Once we calculate our propulsive efficiency and thermal efficiency, we can calculate what will be our overall efficiency. It is nothing but the product of thermal efficiency and propulsive efficiency. So, here in this case what is advised is you just try to remember the formulation what we have used for turbojet engine, and there specifically it is been highlighted here by putting this say TH plus TC. Same way here this is been highlighted with a different color. So, you will not make mistake in terms of writing these equations. Okay. Now, let us try to have one numerical. This numerical, it says we have single spool turbofan engine. You need to calculate thrust, thrust specific fuel consumption, thermal efficiency, propulsive efficiency and overall efficiency. For this engine, it says bypass ratio is 2, compressor pressure ratio given is 8, fan pressure ratio is given 2, core mass flow rate is 15 kg per second. Be careful, it says core mass flow rate. Turbine entry temperature is 1400 Kelvin, diffuser pressure recovery factor is 0.98, combustion chamber efficiency is 96%. Then it says the isentropic efficiency for the fan as 90%, for compressor is 88%, turbine is 94%, nozzle as 95%. There is a loss of 3% delivery pressure in combustion chamber. The total pressure loss in tailpipe is 2%. Let us consider say this engine, it is been tested at sea level where we are considering marked as 0. So, we have atmospheric pressure and atmospheric temperature. It says you select Cp value as 1005 joule per kg Kelvin. gamma value for the air as 1.4. For hot gas, Cp value take 1156 and gamma for hot gas is 1.3 and fuel heating value as 43,000 kilojoule per kg. Now, this data, that is what is been given to you at this moment as a tutorial. So, just try to understand how we have done our cycle analysis, and based on that cycle analysis you just try to solve this numerical. Okay. So, let me give you the hint how do we process with this numerical. So, very first component as we have discussed is our intake. The process we are defining as say infinity to 0 to. We have given information as Mach, temperature, pressure and diffuser efficiency. You can calculate what will be the velocity, temperature and pressure at the exit of the diffuser. Next component we have is our fan. For this fan we have given say fan efficiency, fan pressure ratio, gamma value. We can calculate what will be our exit pressure and exit temperature from the fan. The component next we have is compressor. For that compressor we are given with say efficiency, compression ratio. By using this we can calculate what will be the exit pressure and exit temperature from the compressor. The next component we have is our combustion chamber. For this combustion chamber we are given with say burner efficiency, drop off pressure, turbine entry temperature, Cp value. Based on that we will be calculating what will be fuel air ratio and what will be the exit pressure from the combustion chamber. We have component as a turbine. For this turbine we are given with say mechanical efficiency, say turbine efficiency. We know what is Cp value, what is gamma. Based on that we can calculate what will be the exit pressure and exit temperature from the turbine. We have next component as tailpipe. For that tailpipe the pressure drop is given to us. So, we can calculate what will be the temperature and pressure at the exit of the tailpipe. We have our turbine nozzle, and for that turbine nozzle we are given with say efficiency of the nozzle, mass flow rate, Cp value. We can calculate initially what is the critical pressure, then we will compare that critical pressure with the atmospheric pressure. We can calculate what will be the exit static pressure, exit static temperature and velocity from that nozzle. We have another nozzle, that is what is fan nozzle. For that fan nozzle also we have efficiency, it is known to us, bypass rate is known to us. We will do our calculation for the critical pressure. Based on that we will calculate static pressure, static temperature and the velocity from this fan nozzle. Once we are able to do the calculation for all these parameters, we can calculate the performance parameter for this turbofan engine. So, here I am stopping with, we have detailed understanding of very first configuration, what we say forward fan unmixed configuration with a single spool. Okay. And for that we have discussed about the cycle analysis, then we have discussed about how to do the calculation for the performance parameter, and then we have given with this numerical which you can solve, and we will be discussing the solution for this in next lecture. So, thank you very much for your kind attention.